Thanks to the organizers for such a beautiful and very fun conference. Thanks to the scientific community, well, also for the beautiful conference, and also for giving me the opportunity to speak. So today we'll talk about joint work with Ivan Di Liberti. You can find the preprint, if you're interested, on the archive and the slides on my website. So yeah, let's start giving a little bit of background to this story. So one of the ideas of categorical logic is to use limits and colimits to describe logical operations. And this idea was used in a very nice way and had a lot of fortune, for example, with the theory of topoi. And in particular, just a warning, whenever I say topoi in this talk, I mean rotending topos, I guess. When we have geometric logic, we have arbitrary disjunctions, I always get these two wrong, and finite conjunctions, yes, and distributive rule between them. And in the same way, let's say, we've got the same thing happening in topoi with limits and colimits. Now, if you were a bit eccentric, you can describe finite stuff as up to Aleph 0. Sort of conjunctions. And seeing this in this way, you can imagine how to generalize this idea of geometric logic to, well, lambda-ary geometric logic for lambda any regular cardinal, where instead of having, again, finite conjunctions, we have up to these regular cardinal conjunctions. And Christian Spinola studied the corresponding notion of topoi, which is lambda-ary topoi, where instead of having just final limits, you will also have lambda-ary limits with, again, like a change of the distributive law. Now, one of the aims of this work was to try to find a place where all these different notions of geometric logics, but more in general of infinitary logics, could live together in a place. And in more categorical terms, we want to find a true category where we can embed all of these different lambda-ary topoi and also other categories, hopefully, fully faithfully. Okay, now, one of the three words of the title is classifying, so let me tell you a little bit, remind you what is the classifying aspect of the theory of topoi. So, in logic, we've got, again, a logic, a theory, and then every theory has many possible presentations. Like think, for example, about the theory of groups. You can express the inverse either as an axiom or as an operation. And in categorical logic, the presentations associated to geometric logics are sites. And then when we take the classifying topos of a site, we get what is called, again, the classifying object of this theory. And what I mean with this, we get an object, a presentation of the theory, of the same theory, which is sort of syntax independent, meaning you can imagine all the different presentations sort of to live inside this big, chunky presentation. Now, in, again, more categorical terms, which are the terms that I will use in this talk, which is, let me underline, is not the classical way to see Diaconescu, but we can see this way of the fact that topoi classify geometric logics or in general sites as a reflection of the true category of topoi in the category of Morita small sites. Now, here there is a bi, reflective and not reflective. Don't be scared, it's just that it's an adjunction, but it's a bit weaker than an adjunction. It's a bi-adjunction, and the co-unit will not be an isomorphism, but it will be an equivalence. Nothing too bad. It's still like, imagine a reflection. It's not that crazy. And Morita small, you can just ignore it. There are some size issues. You can't ignore it in the theory, but for the purpose of this talk, just think that is what is needed to solve the size issues. Now, again, the real aim maybe of this work was to try to fill this table, trying to find what could be a presentation for any infinitary logic, and then getting the classifying object. And as you can imagine by the title, the way I will do it, the way we did it, was using sketches and trying to get a Diaconescu theorem for sketches. Okay, so let's talk a little bit about sketches. Luckily, many people, including John, talk about sketches, so my job will be a bit easier. So for a sketch for me is a locally small category, and a little bit different to John, I will not just consider limit sketches, but we'll consider also both a limit part, but also a co-limit part. So we consider a class of cones and a class of co-cones. Then a morphism of sketches, as you can imagine, will just be a functor preserving these two structures, and then we can complete it to a true category, just putting all natural transformations. Quick example. If we have a category with finite products, we can associate a sketch with same underlying category and finite product cones as the limit part, and nothing on the co-limit part. Now, if you take two categories with finite products, and you consider these two, the two connected sketch structures, then you can see that the notion of sketch morphisms between two such things will be a notion of functor preserving product. So let's say the natural, in some sense, way, like natural morphism between such structures. Now, this was not a random example, this was an example related to logic, and it's not the only example related to logic that fits in this context. Also, Lex category, also regular categories, coherent categories, all these different categories connected to the respective logics, like coherent logics, regular logics, blah, blah, blah. The names make sense, luckily. And they all live fully faithfully in the true category of sketches. As you might have noticed, this was not the example that I started with, so we might as well check also that it works for topoi. And indeed, when we have a topos, we can associate a sketch where we take all finite limits and all co-limits as the co-limit part, and morphisms of these sort of sketches will be just morphisms of topoi. Not just for ordinary topoi, but also for lambda-array topoi, we can do the same, just replacing the limit part with lambda-array limits. Now, so the picture is here. I didn't say anything about size. It's a bit more complicated. I will not go into details. If you're interested, there is the reference to sketches of an elephant where they do this construction. But yeah, just trust me that you can do it. It's also fully faithful. We're happy. So okay, we did find actually a true category where all these things live. As you can notice by the number of the slides, the job is not done yet. So we'll have to do a little bit more work. But before that, let me talk about models and Morita stuff first. So again, as luckily John already mentioned, when we have sketches, we have models. And classically, a model for a sketch is a functor into a complete and co-complete category, sending each cone to limits, each co-cone to co-limits. Now, this, in the notation that I gave you, is the same as a sketch morphism from our sketch to the sketch with just the category, all limits as limit part, and all co-limits as co-limit part. And we call these test sketches. The name might not be great, but we couldn't find a better name. And the idea is that if we want to test if two sketches have the same models, we use these sort of sketches, classically at least. But as again John said, I was very happy about that. There is actually no reason, there is some reason to consider these sort of models, but there are, I think, also some reason to consider other models, like models in other sketches, not just these sort of test sketches. So we introduce this notion, we give a name to this notion of when we fix a subcategory of the category of sketches, and we say that a morphism of sketches is a M-Morita equivalence when it induces an equivalence between the models in this subcategory, meaning sketch morphism from S to M for every M in this subcategory. And just a sanity check again, if we take M to be test sketches, we get back the notion of Morita equivalence in the classical sense, let's say. Now, if John didn't convince you, you still might wonder why this thing is useful, and my answer will not be now, will be in a couple of slides, so you need to be a bit patient. Now, okay, let's get to the juicy part of the talk. So, as I was saying, the idea of categorical logic is this thing of representing limits or logical operations, but it doesn't end there. For classifying theory, at least, there are another couple of things that we would like. One of them is some sort of co-completeness, usually, and the other is some sort of exactness condition, some sort of nice interaction between the operations that we have. A little bit like the distributive rule that there is in geometric logic. We will start with the first one and then proceed with the second one. And for the first one, we introduce what we call left sketch. Left goes to the co-limit part. And a left sketch for us is just a sketch with co-complete category, and where the co-limit part consists of literally all co-limit diagrams. Now, we want to get some classifying stuff. So we want to start with a sketch, and we want to construct another sketch, a left sketch, which has the same theory. So we want to get something co-complete, so the first thing that we do is to go to pre-shift, which seems...
Sorry, you've been using the SKT with the capital and lowercase. It has no significance, does it?
No, it does.
Oh.
It was a hidden meaning. So the small is for small stuff, the big is for locally small. Thank you. I will do this construction for small stuff because it's a bit easier. You can do it also for other things. I will not do it now, you can find it in the paper, but thanks. So yeah, if we take something small, then we can embed it in the pre-shift. And now we've got something complete, but we've got a problem because we want the co-limit, the co-cons specified by S to be co-limits. And there might not be co-limits here. And so how do we solve this problem? Well, we look at them in pre-shift where the co-limit will exist, and we say, well, you really should be a co-limit. So we force them to be co-limits, inverting the canonical arrow that will be there. So we look at the co-cons in pre-shift, we look at the co-limit, there will be a universal map comparing these to the co-con and the co-limit, and we invert them. And we can do this in two ways. We can take the orthogonal subclass, or we can also just literally invert maps. Okay, this is a category, this is not a sketch. So let's define the sketch structure on this left sketch classifier. The first thing that we must do is just consider all co-limit diagrams as co-limit part, because that's the definition of left. And then we will consider the minimal structure making this map, this functor, let's say limit sketch morphism. This might not be super clear. It's actually quite simple in this case, because it's just taking the image of all the cones in S. Basically, we are transporting all the second part that we didn't have. Nice. So before checking that this construction does classify, let's take a step back, look at something that we already know classify, and we already know that topoi do fit somehow in this story. So let's see how these things that I just described you relate to classifying topoi. So the question is, if we go from sides to sketches, we do the left sketch classifier, do we get something, do we get the same thing? Does this diagram commute? The answer is, yeah-ish. The answer is yes, but I put a true cell in gray because there is actually a true cell in the middle of this diagram, but I will explain now why I mean with it does actually commute. Well, the first thing, the category is the same. So, at least the only difference is in the sketch structure. But is it a big difference? Well, not really. Why? Because actually, if we reduce to topoi, the models of the two different sketch structures that we find, they are always the same. What I mean, using the notation that I introduced at some point, these two cell will be a topoi Morita equivalence component-wise. So the two sketch structures are not actually different if we just look at topoi. We see the difference just when we go out of topoi. Which, I don't know, I think it's kind of interesting. Now, let's see if they actually classify something. So, first of all, just to check, they do have the same models. We did manage to do a decent job. The cones just came from S, and also the co-cones also were fine. So that's good. So it's a test Morita equivalence. But it's not just a test Morita equivalence. They don't just have classical models in the same way. They also have the same models in any left sketch. And again, I think it's kind of interesting because we did a left sketch construction, and what we find is a left Morita equivalence. So I think I'm not really sure what's going on, to be honest, but I think something interesting is going on with this parametric reasoning. Now, again, we need to get at the Arconescu theorem, we need to fix size issues. The way we did it was to consider Morita small stuff, which would mean a sketch that is Morita equivalent to a small sketch. And if you consider this Morita smallness, then we do get a bireflection, just like in the case for topoi. And so we get the left sketches through this construction are bireflective in the true category of Morita small sketches. And again, this construction can be extended to Morita small sketches. It's a bit harder, but not too different. So if you're interested, again, the paper. Let's go. Okay. I promised to talk about classifying logoi, so we shall talk about logoi at some point, even though the slide doesn't start with them. So I mentioned that we have these two things. We have co-completeness, which we sort of modeled with left stuff, and now we want also to model some exactness. We want to describe when the co-cones and the cones, they interact in a nice way. So the way we found to describe this was to using left rounded sketches. So the left is just because we're doing everything focusing on the collimate part. You could also do everything focusing on the limit part. So I will drop the left because it will be a bit redundant now, but just remember that you could also go to cones instead. So this definition might look weird, but I will give it anyway, and then I will give a description that might look a bit more clear. So we say that a sketch is rounded when, if we consider the left sketch classifier and we consider this J modifies all the cones, sends all the cones in S to limits. So you see the interaction between limits and colimits because S was a co-completion in some sense, let's say. So working on the colimit part, and here we're saying, well, actually interacts nicely in limit with the limits as well. So just to not go crazy, we do have a lot of examples. Basically all the categories that I talked about, they do embed in rounded sketches, not just in sketches. And again, as I promised, let's see another characterization. Well, it might be a bit clearer, I think, at least for me it was a bit clearer when I realized that this definition of rounded is the same as saying that the head construction, the left sketch classifier, is normal. So normal for a sketch means that both the cones are all of colimit form, and the co-cones as well are of colimit form. And so a left sketch is always left normal because the colimit part is always of colimit form, but it might not be of also right normal, let's say. So rounded literally means that actually the left sketch classifier becomes normal. So the limit part will consist of limits. A little property of rounded sketches which will be very useful in a second is that if you start with something rounded and then we do the left sketch classifier, we also get again something rounded. It's actually not even that hard to see this because basically the idea is that if you repeat head, if you apply the left sketch classifier to a left sketch, you get something equivalent. So this is the little trick that you play here. Now finally, let's come to our proposed at least definition of logos. So logos is a word that has been used a lot in category theory. We are sort of continuing this tradition, started with Freud, who used this word for describing something that now is called, I think, a heightened category. Then continued with Joyal and Anel, who used it for the true category of topoi. We propose this definition because we think it fits quite well with this sort of tradition, and we sort of try to extend it to infinitary logic. Might be a bad idea, I don't know. But this was the reason why we use this word. So a logos for us is a rounded and also left sketch. So putting together these two different properties that I was telling you about. As an example, just to not go crazy, topoi, they are logos, and I mean you can see it because I just told you that they are rounded, and you can see by the definition that I gave you at the start that they are also left because the colimit part consists of all colimits. Not just topoi are logos in this sense, but also lambda array topoi are logos in this sense, which I think is kind of nice. Now, let's get to the main result now. What we proved is that, again, when we restrict to Morita small stuff, we managed to prove that logoi are bireflective in rounded sketches. And what I think is even nicer is that this proof is not that crazy once you've got all the prerequisites that I just told you about. Because the way we did it was, well, we consider the Diaconescu theorem that we already have for left sketches, and then we restrict to rounded sketches. Now, logoi, they are also left, so this picture makes sense. What is nice, and the head construction, as I told you before, if we take a rounded sketch, then the left sketch classifier would be left, will also be rounded, and so it will be a logos. And, I mean, the job is not done, but you can see that actually this biadjunction reduces to a biadjunction here. So, I think it's quite nice. What is even nicer, I think, is that we can see the first Diaconescu theorem that I told you sort of living inside of this one. Because Morita's small side is around the sketch. I mean, yeah, I didn't use it as an example, but trust me. And topoi are logoi. And so we sort of see this nice picture coming along. And for those of you who also know lexical limits, the theory by Luck and Gardner, also there by reflection of between phi exact categories and exact categories, it does also fit in this picture, making this very big and kind of cute diagram. Now, to wrap up, let's go back to the table that we wanted to fill in. And just to summarize, the way we, at least the suggestion of how to complete this table at the moment is, well, as presentation we can take rounded sketch, and the reason is because, I mean, all the examples that we had, they do fit with this idea, and as classifying object, logoi with our proposed definition, and we've got this Diaconescu result connecting them and providing the classifying object for any theory. It was a bit early, but I think I'm done.
Questions, comments?
Hi, thanks for the talk. So, you're getting infinitary logics, but without. So you're not getting intuitionistic logic with a heightened implication in this framework, are you?
I don't think so.
Have you got any ambitions, or do you have any ideas how that could be fitted in within this sketch framework?
No idea, but sounds interesting. I will talk with the more logician part of this collaboration.
Well, sort of picking up on the heightened bit of the previous question. So sketch theory was developed by a rather inward-looking French community, which I think is now extinct. But they must have a lot of good stuff there in their own private journal diagram. But I mean, they did go beyond just limits and co-limits. I think Pierre Ageron, who long since left category theory, had stuff about Cartesian categories. So, I mean, what I'd like, sketch theory is sort of a categorical language that might correspond to some symbolic logic and proof theory, right? So it could, it could be something that could be developed so that we have something to talk to proof theorists about.
Was that a question? It was very interesting.
Yeah, so with this hat construction, you first take pre-sheaves, like the free co-completion, and then you kind of formally make the co-limits the same, so you ensure that they're coming from the co-cones that you want.
Almost. So what we do here is that we force everything coming from here to be a co-limit.
Yes.
But they might not be all co-limits.
Yes, yeah. So do you have some result that this is like the free category that's co-complete and that sends the co-cones over here to co-limits?
I guess in a way maybe you could see the Diaconescu theorem in that way, but not 100% sure. But I guess, like this result, in my intuition, which is, not the best logic intuition ever, but my intuition, this left adjoint is sort of doing that. Again, I guess the question is this framework really representing what you're saying? And the answer is, hopefully.
So I was wondering how this compares to Mike Schulman's paper on small sheaves and exact completion. So I think there he's basically working with what you call rounded sketches, and it shows that shows that what you call logoi are kind of reflected in that.
Yeah, I think there are some connection. These left rounded, we didn't pick it up randomly. Like we saw at examples, we saw at like your paper, and something like this appeared. I think Schulman does something a little bit different, but now I don't remember that paper too well. I would need to go back. I think we did discuss it at this point, which might have been 1 year ago. But yeah, maybe we can talk about this another time. Sorry.
For what it's worth, I vote for Anel Joyal's use of the word logos. I think it's a pretty good use of a word that we might keep.
We might change it. We're not. I at some point regret using this. I already submitted the title as okay. But yeah, we are not. We didn't want to criticize anyone. We're not really inventive with words. So
I agree that Bride's use of it is now. I think they made a good proposal.
yeah. We will try to find another word. Again, like we didn't want to criticize anyone. Just yeah.
You're open with the goal of this being to have a two-category where these variants on Logoi live, and it seems like you've succeeded, but is there anything new that lives in what you've ended up with, this category of rounded sketches, which is not just lambda Logoi for some infinite lambda? Do you have other new things that live in there?
Not that we don't, but I guess probably. Yeah, we checked the examples that we had, but yeah, at some point maybe in the future it would be interesting. But yeah, for example,
Concentrating on lambda topoi. In a sense, you are extracting a full subcategory, a subcategory of topos bounded over preferred topos. Do you know anything of the closure properties of this subcategory that you could generalize to another base?
No, but I think it's in Espindola's paper. Christian Espindola, because he studied, with also some collaborators, he studied these sort of structures. And I think it does do a little bit of this.